Okay, in this lesson, we're going to look at random samples. Let's start with just what a representative sample is. So I kind of broke a rule here and I used the word representative in the definition, but a representative sample accurately represents the population. So it should look like the population. It should have features just like the population does. So for example, if you grabbed a random bunch of people from Walmart, that's probably pretty close to the population. But if you took maybe a sample of doctors or neurosurgeons, you may find that they don't accurately represent the population just in their background or their ethnicity or the country they're from or anything like that. So a representative sample can be nice. A random sample, however, or a simple random sample we'll start with here, can be useful statistically. A simple random sample has two properties. First of all, every element in the population has to be equally likely. So no one's more likely than anyone else to get selected if it's people. And also, every sample size n, or n can be any number, has an equal chance of being selected with it as any other sample size n. So every sample size 10, for example, would be just as likely as any other sample size 10. And that you could get a bad sample. You could get 10 basketball players or 10 little people, or you could get 10 people with PhDs in something. You know, it's just the second simple random sample part. So if those two both are met, these conditions 1 and condition 2, then we say we have a simple random sample. And a simple random sample is very nice because we can use some statistical equations with it. So it should be obvious to you why the first condition is required. I mean, you want everything to be able to be selected. You don't want to rule people out. But the second one's a little less obvious. Sometimes working through a couple problems here and looking at examples makes it sense, and will enlighten you on the second condition. Let's talk about producing 9 light bulbs. And we're going to take a sample of 3 systematically using a technique. We're going to take one of the first 3, and then every third bulb is taken. So if we have our bulbs, there are 9 of them, 3, and I'm going to label them 5, 6, 7, 8, 9. There's 9 bulbs. One of the first 3 we'll take randomly. So we'll either get 1, 2, or 3. And when we sample, so if we chose 1, we'll call this sample A, and B, and C. For A, if you randomly chose 1 here, then every third one, 2, 3, you get 4, 5, 6, 7, and 7, and 8, and that's it. If you started with 2, if that was one of the first 3 randomly chosen, then every third, 3, 4, 5, 6, 7, 8. And then 3 would be 4, 5, 6, 7, 8, 9. So your samples, you could have the first, 4th, and 7th bulb, the 2nd, 5th, and 8th bulb, or you could have the 3rd, 6th, and 9th bulb. And I say, oh, you know what? Every bulb has a possibility of being chosen, and every bulb has a possibility of being chosen only once. So it looks like it meets condition 1. Good. However, there are some sets you cannot get, like you'll never get bulbs 1, 2, and 3. So it fails condition 2. So it's not a simple random sample. Or no on this one. And that may give you a little consternation because you might say, well, that's exactly how I'd want to sample them, even if it isn't simple random. And that's true in a production system. You would want to do something like that. However, it's not a simple random sample. Let's try this next one, 15 team jerseys. Put 15, and we're going to assume they're all the same size. And they're put in a washing machine that mixes them very well, runs, and then we pull out 3 jerseys. Does it meet the 2 conditions of a simple random sample? So for the first condition, are you just as likely to get any jersey as any other one? And hopefully you see the answer is yes. How about the second condition? Is there any group of 3 jerseys you cannot get or that's less likely? I think you can see they're all just as likely. any group of 3 jerseys would be fine. So in this case, n is 3. 6 lotto balls. So let's think about the conditions there. Is every lotto number equally likely? We're going to say yes. There's some people that try to use techniques that don't assume that, but I'm not sure about that. So 6 lotto balls. So every ball is as likely as any other ball, but is every group of 6, so in this case n is 6, equally likely? You say, well, could you get the group 1, 2, 3, 4, 5, 6? You might be highly suspicious if you did, but you could still get it, and they should all be equally likely. So both of these two, the answer is yes. They're simple random samples. Let's talk about cards briefly. So there's let's say it's a standard deck, 52 cards, and you're going to shuffle it and draw 5 cards. Then you replace and you draw 5 more, and you do that 10 times. So you've got, I don't know, 5 cards, and then you've got 5 cards. So you've got you just note down which 5 cards each time. So you'll have 10 hands or 10 draws of 5 hands. And does that meet the 2 conditions? You say, well, is any hand possible? Sure, you could get anything. You could get a royal flush and spades. You could get a straight. You could get just a bunch of trash. I mean, a pair of 2s and a pair of 3s and a 7 or something. What about the second one? Is every sample of size 10 in this case equally likely? So let me just throw one option at you. Let's say you got a royal flush and spades on that first draw. Could you get the royal flush and spades again on the second draw? I think you say yeah, because you replace the cards back in, you shuffle it, and you could do it. So you could even get the royal flush of spades 10 times in a row. And so, yes, if there's any hand you have, you could certainly get it again. So that is a simple random sample. Of course, if you got, royal flush of spades 10 times in a row, you'd be much more likely to get hit by lightning or a meteorite or something. But that one works. Now let's twist that one a little bit here for part E. And this time it's the same, except now if you draw the same hand a second time, we're going to not count it. We won't write it down. We'll just draw again. So that way, what do you think? Is every hand equally likely to be drawn? And you say, well, yeah, you could draw any hand. But the second one is every sample of size 10. You say, well, could you have the sample royal flush of spades twice? And the answer is no. So that sample could not happen. Oh, sorry. No, if any one of the conditions is not met. And then let me just sort of try to get you to think about another thing for a moment. Let's say that a die is rolled. What's the population? Does that make sense to you? If I ask you what the population is, you might say, oh, you roll a die. I've seen the students always want the answer. You say, well, what about 1, 2, 3, 4, 5, and 6, right? A die has 6 sides, number on each side. So that sounds kind of like the population. And what if you rolled it twice? Then you'd have, oh, what's the population of 2 dice? Well, you got roll 1. And we'll do this later on. I'm just trying to introduce this so you're familiar with it. For roll 1, you could have 1 through 6. And for roll 2, you could have 1, 2, 3, 4, 5, 6. And that means, if you kind of look at this, we could draw what we call the sample space over here. So you say, well, you could roll a 1 and a 1. 1 and a 2, a 1 and a 3. These are all the kind of outcomes here. 2, 1, 3, 1. Each box in here shows there's 36 possible outcomes that are different. And they're all equally likely. But does that make sense? And it's not really called the population. We call that this sample space. Like, what are the possible things you could get in a sample? Or you could call it the outcomes. So population and outcomes is a way to distinguish probability from, or theoretical probability from statistics. And so these dice rolls, the reason that's a little confusing based on our other sample and population comments, is because they're probability experiments, and I've left the realm of statistics and I'm in pure theoretical probability right now. So as you can see, we have outcomes instead of a population, and we'll look at that later on. But for now, let's just have a definition that separates statistics and probability. Statistics is using a sample to describe a population. It involves sampling methods and, of course, error management. Probability involves calculating the chances or odds that an event will occur. Like, what is the odds that I draw a royal flush out of cards? Or what are the odds that I roll an even number on the next one or something like that? Or roll a 7 or an 11 if you're playing the game of craps. Some popular sampling methods, and these are just a few, and there's all kinds of intermediate ones, but they're systematic, stratified, proportional, and cluster. These are the classics. So systematic is where you randomly select a first sample, and then you take every, like the light bulbs, like you randomly select one of the first 3, and then every third one. And that's very useful in production lines, because you know that fixed K is the most errors you'd have before you checked and could fix a problem. A stratified is where if you have a population, if you picture a population and you have people and you split them by something, like this could be actually physically where they live. You might have the rich, the middle, and the poor, and you might say, well, I'm going to take a fixed number. I'm going to take 10 out of each. My sample size will be 30, but that way I make sure I count everybody. And sometimes, though, you don't really want to take 10 out of each, so that will be stratified. You might actually look more like this, like rich, middle, and poor. You might want to take, like 5, 15, and that's maybe not too good, 10, and 15. So there's 30 again. But this time, we still stratified it, but we realized that there were fewer rich people, so we took a smaller proportion. And so it's like stratified, but being a little clever. And then cluster sampling, and that's some of, but not all possible subdivisions. So if you have a lot of, divide your data set. I'm not going to make a pie chart anymore. I'm going to make it look weird. If that's your data set, you might not select this one because it's hard to find those people or something like that, or there are not many of them, or they're not affected by whatever you're testing. For instance, you may not want to test a whole bunch of people that can't get a disease because of a genetic reason. They have a genetic marker, so they can't get a disease, so maybe don't test them so much for the disease. Choose what you think is the best sampling method. So here I have a few examples that'll help clear up these 4, and then you can see at the bottom here, I've kind of encoded the answers. So the exit poll, if you're trying to see how people voted in an exit poll, if you stir on it for a little while, you can see, well, it's not really a way to cluster. I mean, would you just take them at different times or something? But probably systematic would be the best on that one. And light bulb production line also. And computer packets. Those are those little things, when you're talking on your phone. Don't really have an antenna anymore, but it goes to the tower, right? And that goes to this thing we call the internet, which is this network of computers, and gets packets, and then it goes to some other tower, and then somebody else's phone. And what travels along there are these little packets of information, and you might want to check them. They have little check bits in them, and you can see if they're right and correct things along the way, because every computer transfer is a chance for a bit to get flipped in there. And if you're testing those, again, that's going to be another kind of systematic thing. You can just imagine these little packets flying along, kind of like if you saw that I Love Lucy episode with the chocolates. They're coming along, and so you kind of want to check before too many go by and you lose the information. General political polling. Now there, systematic doesn't almost sound right, because political polling, you often have maybe the country. There's a terrible United States for you, and there's other stuff too. There's, we should be other parts of territories. So if that's the United States, you might want to say, well, how am I going to poll that politically? It might depend on what you're looking for in there. So systematic's not going to be easy to do, but you can see geographically that fits to stratified, maybe by state, or another way to measure people online. Or proportional, you might, hit more people in the areas with more people. Texas is almost there. And then cluster sampling, you might say, oh, well, maybe I'm just interested in groups of people here and here and see what happens. So you could say maybe systematic or stratified. I'm sorry, I wouldn't do systematic. Stratified, proportional, or cluster on that one. And M&M consistency, think about that a little bit. Let's say in this case for M&Ms we have red, green, blue, yellow, brown, by color. We'll do it by color, make it interesting. So here, you may not want to do systematic because they may be coming in, you don't want to accidentally check every red one or every green one or something like that. So you're going to want to somehow do some kind of stratified, some of each color, or proportional, like maybe there are more red ones and more black ones in there for some reason. I think they are actually, if you count them. You'll want to proportionally see more. So maybe you'd say statistically stratified or proportional. And you probably wouldn't want cluster sampling. You don't want to leave out like the yellow M&Ms because then you end up with a bad batch of yellows you would never know. And then worldwide approval of U.S. policy. That's one I kind of threw in, like maybe cluster on that one. And the reason is because there's some countries, they keep changing everything. They just may not be able to be measured. So you might want to just eliminate those if it's too hard to get an answer fast enough. And is the following correct? A correct definition of a simple random sample. So let me just come back and see. A random sample is a sample selected such that every element in the population is equally likely and every sample is equally likely. Is that true? You can see that's condition 1, but we left out of size n. So nope, is the answer to the question. It needs this part. Because a sample of size 20 would maybe not be as likely as a sample of size 3 or something like that. All right, thank you. See you next lesson.